please let me know when you'd like me to start.
We are trying to get it connected to YouTube because I think we have more than the capacity for this space is not taking in everybody. So we're trying to live stream it on YouTube.
Yep.
I think that is working already. So I'm going to start recording now, sir.
Terrific. So let me begin by introducing myself. I'm David Spergel. I'm currently president of the Simons Foundation, which is a foundation in New York founded by Jim and Marilyn Simons that provides support of basic research in math and science. And while our support is primarily to researchers in the US, we support institutions and researchers worldwide in basic math, research, science, and also we have a program in research on autism. I have spent most of my career at Princeton University, where I was a professor and then eventually department chair. And what I'm going to try to do today is give you an introduction, a very ambitious one in many ways, to two topics in a sense. One is cosmology, and in particular, the study of the microwave background, the leftover heat from the Big Bang, and how we use it to determine the basic properties of the universe. And then I also want to introduce the statistical methods we use. And in doing it, I really want to accomplish two goals. One, for those of you working on a sense on any scientific or engineering problem where you have a model and you want to fit parameters to the model, I want to show you how you can use techniques that work well when you have a likelihood for the data, when you can estimate the probability of seeing the measure, getting a given measurement, given the model and parameters. And I want to introduce cosmology and talk about how we apply it. And in my second lecture, we'll look at another problem in cosmology, that of large-scale structure. And there I want to introduce machine learning techniques and show how we can use simulation-based inference as a mechanism to infer information from data. And again, I think the goal is really twofold. One, to introduce you to cosmology, and the second is to show you the statistical methods that one can use. So the basic problem, and this is Reverend Bayes and the famous Bayes equation, is given a model with parameters, how do we determine the parameters that fit the data? And for here, we'll make use of Bayes' theorem, which says the probability of A given B is the probability of B given A times the probability of A divided by the probability of B. And when we apply that to our model, our data, what we'll want to do is we want to compute what we call the posterior, which is the probability of the parameters in the model given the data. Oops. Let me just move this off my screen. And that's equal to the probability of the data given the model times what we call the prior, that P naught of A. What do we know about the parameters in advance, divided by the probability of the data. And in most cases, that the denominator is just a normalization factor. So then we can rewrite this as the probability of the parameters given the data is what we call the likelihood of the data given the model times our prior. And this rather, in a sense, simple equation encapsulates much of what we want to do in data analysis when we have a model and we want to ask, how do we determine the best parameters? Now, often we have in our model parameters that we're interested in In our case in cosmology, things like the age of the universe or the density of atoms in the universe, parameters that have real important physical meaning. And then we'll have what we call our nuisance parameters, things that often are characterizing our experiment, but are uncertain. Things like the resolution of our telescope, which might have some uncertainties in it, uncertainties in how accurately the telescope points. If we're observing through our galaxy, as we often do, we always do, but at certain angles, we have more galactic emission or less. Things that characterize our galaxy. And in almost all measurements you make, we have what are called nuisance parameters, parameters that we are not interested in for their own sake, but they have an effect on what's measured. They're often calibrations in a measurement or so on. And there's uncertainty in those. And we want to marginalize over those uncertainties. And that's what this equation describes. We take our likelihood, we multiply the prior, and then we integrate over our nuisance parameter dB. And this is what we call marginalizing over the nuisance parameters. And that's what we'll do in these problems. Now, I've mentioned priors. What are priors? Priors are assumptions that are informed by previous data. Sometimes we might want to make very conservative assumptions, not assume that we know much. But even in those cases, sometimes we have parameters, in our case in cosmology, parameters like the density of the universe, its age, the rate at which the universe is expanding, that we know are positive. So we can put down a simple prior, that's a positivity prior, that says P of A is constant for A greater than 0 and equal to 0 for A less than 0. Often, when we don't have much information, we'll make use of logarithmic priors. And sometimes we'll use flat priors, where we assume each value is equally probable. If you look at physical constants or properties of atoms, you'll see that when you're drawing from some physical distribution, it's often true that a logarithmic prior better represents your data. Sometimes we might want to use more restrictive priors, make use of information we have from previous experiments, and use that to inform our analysis. One of the things we want to look at is, after we've done our analysis, our posterior and our prior. And if our posterior looks remarkably like our prior, then our experiment hasn't informed us very much, and we haven't learned too much from it. Often we're going to want to compute the maximum likelihood value. And here I'm putting in a flat prior to make things a little simpler, and say, if I have a flat prior, it simplifies to the probability, the posterior on A is just the likelihood of the data given the model with parameters A. And we could talk about a maximum likelihood value, and that's the value that maximizes the likelihood. Hence, the derivative of the likelihood respect to A at that point is equal to 0. And that's the and often in the discussion of models, you'll hear people talk about the maximum likelihood parameters for those models. And if we want to determine the uncertainty in those parameters, we take the likelihood function and expand it out in a Taylor series. And it's convenient, instead of working with the posterior or the likelihood, to work with their logarithm. And here we've written things out where we've done a Taylor expansion in log P of A around the maximum likelihood point. And you'll notice in this Taylor expansion, the second term, the derivative of log likelihood with respect to A, isn't there. And that's because we're at the maximum likelihood point. And recall that at the maximum likelihood point, we saw that the the first derivative is 0. So then the next order term is the second derivative term, that term here. And this second order term is often expressed as the Fisher information matrix. We define Fij as the second derivative of the log likelihood with respect to parameters. And that characterizes our uncertainties in the parameters. And you can see that if we ignore our higher order terms, we can now write down our posterior, the posterior of A, how likely any parameter it is, as the probability of AML, maximum likelihood, times a Gaussian centered around the maximum likelihood value. And think about now taking that Gaussian and simplifying this so that we have a model with only one parameter, so that that exponential is the exponential times -1/2 f11 delta A1 squared. And then the uncertainty in a parameter is the inverse of f11. So you can see our Fisher matrix describes the uncertainties in parameters and the correlations between parameters. If we go to the simplest case for the form of our data, where we have independent measurements, each with Gaussian errors, then I can write my likelihood, my log likelihood, basically as a chi-squared, where the chi-squared is the sum over all the points of my model, times the difference between the data minus the model prediction at that parameter, squared divided by the errors. And if I now take that form of the likelihood, compute the second derivative, you can see the second derivative, the Fisher matrix, depends only on the model parameters. And you can see that there. And in fact, this is an interesting result. It says that the uncertainties in the parameters are not going to actually depend so much on the data. Of course, the data determines the maximum likelihood value. But if you have some reasonable guess on what the parameters might be, you can actually characterize from an experiment what uncertainties you expect before you actually make the measurement. And this could be quite useful if you want to make estimates of how effective a measurement can be. And now let's finally turn in this introduction to the statistics to a much more general case where now I have many, many parameters, A1 to A sub n, and I want to marginalize over all the parameters but one and simplify the model. And this shows you the mathematics of how we do this. If we want to marginalize over the uncertainties in the parameters, we integrate over those parameters, integrate over the posterior, marginalizing over all the parameters but A1, the one I'm interested in. In our case where the likelihood reduces to a Gaussian with that Fisher matrix form, I can do that integral explicitly for a Gaussian and then find that the marginalized likelihood takes the form shown there, which is nothing more than a Gaussian whose dispersion is the equation on the bottom. And you can see that the effects of marginalizing over the other parameters given their uncertainties, this term here, subtracts from F1 and has the effect of making the uncertainties bigger. And I'll be happy to share at the end a copy of these lecture notes if people want to go through these equations. But if you don't, the high level picture to take away from this is when you have to marginalize over uncertainties, when things like calibrations, other terms in your model are not well known, those uncertainties will always increase the uncertainties in the core parameter you're trying to measure. And this is why I think it's important when you're doing an analysis to recognize all the pieces that go into the analysis and recognize that uncertainties in those parameters that go into the analysis will blow up and increase your uncertainty in what you want to measure. And this result, well, I'm going to apply it in cosmology, I think is an important one for really any of us working with data, whether it's in medical fields or chemistry or other areas of physics or economics, that when you have parts of your model that are uncertain, they will almost always couple to other terms in your model. That's this cross term here. And if you don't fully incorporate all of your uncertainties in your analysis, you will be overly confident in your conclusion. And I think one of the things I always encourage students to do is try to capture all the uncertainties that go into any of their calculations. So now let's turn from statistics to cosmology. And if I were to summarize the last 20, now almost 30 years of cosmology, I would say what we've learned is our universe is both remarkably simple and remarkably strange. Simple in that the same laws of physics that are valid here in New York, there in Nigeria, are valid on the scale of the whole visible universe. Seems to be true. You can test that, check in various ways. Another is that the total energy of the universe is zero. Equivalently, the geometry of the universe is what we would call flat, that the Euclidean geometry, which you learned in your teenage years, is valid on the scale of the whole visible universe. We've seen that the early universe underwent a period of early acceleration that gave rise to the fluctuations we see on the scale of the sky. And now we get to the strange part. Our universe is composed not just of atoms, which actually make up only about 5% of the universe, but that most of the universe is in the form of what we call dark matter, some unknown particle whose properties are different from that of atoms, but cluster gravitationally, and what we call dark energy, something that seems to fill empty space, and we have no evidence that it clusters at all. It could, in fact, be something like a vacuum energy or a cosmological constant, energy associated with empty space. The remarkable thing is in this model with 5 numbers, cosmologists can fit all of our astronomical data about the large-scale structure of the universe, and, our microwave background data, all the pieces fit together with those 5 numbers. And what I'll be talking about towards the end of the talk is how we determine those 5 numbers. But before we do that, I need to give you some basics of the physics behind cosmology. So let me start by talking about special relativity. Because light travels at a finite speed, we see things not as they are now, but as they were in the past. If you're looking at a friend across the room, he or she may be a few nanoseconds away. It might take light a nanosecond or so, a billionth of a second, to travel from them to you. That doesn't matter much. They haven't changed in that billionth of a second. Looking further afield, look out towards the sun, you see the sun not as it is at this moment, but as it was about 8 minutes ago, because it takes light about 8 minutes to travel from the sun to us. When you look towards Jupiter, it might take more like 40 minutes for light to get from Jupiter to us, or maybe even a couple of hours, depending on where it is in its orbit. And the further away you look, the further back in time you look. When we look at a nearby star that might be 5 light years away, we see it as it was 5 years ago. When we look at a galaxy like the Andromeda galaxy, we see it as it was 1 million years ago. And when we look with the James Webb Space Telescope at a distant galaxy, we might see it as it was 12 or perhaps even close to 13 billion years ago. Now that we understand special relativity, let's turn to general relativity. And the key ideas in general relativity is that matter tells space how to curve, and the curvature of space tells matter and radiation how to move. And in this picture, you can see the famous effect of the deflection of light around the sun that happens in an eclipse. Oops. And here's a report from over 100 years ago from the New York Times describing the first observation of the deflection of light. As they say, stars not where they seemed or were calculated to be, but no one need worry. Well, they were in fact exactly where Einstein said they would be. They reported that only 12 people at the time understood general relativity. The joke about Eddington, a famous British astronomer, was at that time, I think he was told, Lord Eddington, I hear only 3 people understand general relativity. And Eddington reportedly said, yes, who's the third? So, but now I think we can many of us can understand and do this. We can frame this and understand what general relativity implies. And one of its key implications comes with the expansion of the universe. So let me now talk a bit about redshift and how we measure the universe's expansion. When we look at a nearby star, we can measure spectral lines. Here we show some absorption lines that might be in the atmosphere of a star. And all the atomic absorption or molecular absorption lines or ionic have characteristic frequencies. Because of the Doppler effect, those lines shift. The amount they shift, their redshift due to motion, is equal to the velocity divided by the speed of light. That's when you're looking at relativistic motion. One of the predictions of the let's start with the observations. One of the observations that really led to the establishment of our expanding universe model, sometimes called the Big Bang model, but I think it's better to think of it as the expanding universe model, is Hubble noticed that a galaxy's velocity depends on how far away it is. And that's Hubble's data on the left, some modern data on the right, looking at type 1a supernovae, and you can see the relationship between distance and velocity. The further away a galaxy is from us, the faster it's moving away from us. Of course, we can now turn this around for more distant things, and given the measurements of velocity, infer what their distance is. And this is all part of what we call an expanding universe. And to me, this is conceptually the most difficult part of cosmology, because I think we all have kind of an absolutist Newtonian notion of space and time. And when we think about, say, things like what is the universe expanding, the immediate question we get is, what is it expanding into? I like to think of this as the universe is expanding into the future. And the picture I have when I think about the expanding universe is, rather than think about a 3-dimensional universe, which I think is hard to visualize, I think about an expanding 2-dimensional universe. I think about us as living on the surface of a sphere, and every galaxy being on the surface of a sphere. And as the universe expands, the radius of that sphere gets larger and larger. And you can think of that the radius of the sphere corresponding to the expansion factor, or alternatively to the age of the universe. So as the universe gets older, that sphere gets bigger and bigger. That expansion factor grows, the universe gets less and less dense as it expands. And that lets us run things back in time as the universe gets younger, as you go back towards what we call the Big Bang. The universe gets denser and denser, hotter and hotter, and you can see that sphere eventually, we let its radius go to zero, collapses to a point. But notice that it collapses to that point everywhere in space. That entire sphere collapses down to a point. And if we take this in 3D and think about our expanding three-dimensional universe, if we run it back in time, the whole universe collapses to one incredibly highly dense point. And in principle, infinite density, if their equations are valid to that point, which we don't think they are. But as we run this back in time, you'll notice that this initial singularity, where the Big Bang happened, is not a place in space, but a moment in time. It happens everywhere in space that you reach this density. We describe this expansion by what we call the Friedmann equation that relates the expansion rate, or the Hubble constant, to the density of the universe. So now let's review this basic picture we have in cosmology. The universe starts out incredibly hot, incredibly dense, filled with radiation. As it ages, it expands, becomes lower density. As it becomes lower density, it cools. During the first few minutes after the Big Bang, the light elements form. Hydrogen forms, merges into helium. Much of the lithium in the universe forms in those first minutes. After about 500,000 years, electrons and protons assemble to form atoms. And roughly about 100 million years after the Big Bang, stars start to form. And galaxies and quasars and many of the larger structures really emerge about 1 billion years after the Big Bang. Today, at present, we're about 13.8 billion years after the Big Bang. And let's then turn to what we call the microwave background, the leftover heat from the Big Bang. And this shows a picture of the evolution of the universe as it expands, with its beginnings starting on the left on the plotted on the axis is redshift, or it's when the universe is 10,000 times its present 10,000 times in redshift, so 10,000 times higher temperature, hence 10,000 cubed, or about 1 trillion times the current density. The universe was fully ionized. The electrons and protons were dissociated from the hydrogen. About 500,000 years after the Big Bang, the universe gets cool enough that the electrons and protons combine to become hydrogen. That becomes transparent to this cosmic background photons, and they can then propagate freely from then to now. So when we go to observe the microwave background, the leftover heat for the Big Bang, what we are really doing is looking back in time, 13.8 billion years, and seeing what the universe looks like back then. And one of the things I've been involved in is making maps of the microwave background, the leftover heat for the Big Bang. And there's been a series of maps made over the past couple decades, starting with observations with the NASA satellite COBE, that made observations in the 90s, observations that would earn its leaders the Nobel Prize, followed by our own satellite, the Wilkinson Microwave Anisotropy Probe, or WMAP, a NASA-launched satellite that I was part of. And then about a decade ago, the Planck satellite was launched by the European Space Agency in collaboration with NASA. And this shows an image of the Planck satellite with a map of the fluctuations of the microwave background. While the microwave background is nearly uniform with a temperature of about 3 degrees above absolute zero, there are tiny fluctuations in the microwave background, tiny variations at the level of a few millionths of a degree, tens of millionths of a degree, in the temperature of the universe from place to place, representing variations in density from place to place, and those fluctuations are shown in the map. And what I want to turn to in the remaining 20 minutes of my lecture is how we study those fluctuations and use them to determine the basic parameters. So first, let's look at the data. Here's the data from the WMAP and Planck experiments. And at this resolution, your takeaway should be, hey, those pictures look the same. That's good. And that's actually a tremendous accomplishment when independent experiments see the same thing with very different instrumentation. It's really reassuring to see groups confirm their results. Now let's go to analyze the results. The first thing we do is let's look at the distribution of temperatures. And you can see the temperatures. This is in the WMAP data. It's actually from the first year of WMAP data. The data is smooth with angular resolutions of 4 degrees, a degree, and a quarter a degree. And you can see that the histogram of points is very nicely fit by that dashed red line, the Gaussian. So once we've done that normalization, there's actually no free parameters in that dotted line fit to the data. And it's one of the pieces of evidence that suggests that the universe began with Gaussian initial conditions. This is a remarkable statement. This actually says our observations imply that the universe began in a remarkably simple state, and all the complex structure we see arises through gravitation acting on this very simple universe. And how that structure grows and how we characterize it will be one of the topics of the lecture, my next lecture in this series. And the properties of these fluctuations are remarkably simple. The basic fluctuations, let's go back to this equation. We take the density fluctuations, we expand them out in a Fourier series, and then say they're Gaussian, which means the information is encoded in a power spectrum. And that power spectrum is really simple. It's described by 2 numbers, an amplitude and a scale dependence. And all the other basic properties of the universe are described by 3 additional numbers. Its age, the density of atoms, the density of matter. And this model, with just those 5 numbers characterizing the universe's basic properties, can fit not only the microwave background observations, but our observations of the large-scale distribution of galaxies, the universe's expansion rate and abundance of elements, many of its properties. What we'll do in characterizing these maps is we'll write down some summary statistics, the 2-point correlation function of the map, because it's a Gaussian field, and these really capture all the basic properties of the map. And we don't have time to delve into that, but we can compress everything to basically the variance as a function of scale. And as I've mentioned already, while the model is simple, it's also rather strange, with dark matter and dark energy making up most of the universe, and only about 5% of the universe in the form of normal stuff. There's other important questions we want to answer about the properties of the universe. Our model doesn't answer how the universe began, whether it's unique, how it will end. And we'd like to understand more about this very rapid period of fluctuations called inflation that leads to the fluctuations we see. So in addition to operating those satellites in space, one of the things I've been involved with is operating a telescope in Chile called the Atacama Cosmology Telescope. It's located in Chile in the Atacama Desert near the border with Argentina and Bolivia. I am part of a large multinational collaboration that's been working on this Chilean experiment, and we're now building its successor. My Simons Foundation had, I'm very involved with the Simons Observatory, which will make the measurements you've seen, you'll see in the last few minutes, with even higher precision, improvements in precision and sensitivity of nearly an order of magnitude over the data we're about to discuss. So here's the measurements from the Planck satellite. Here's measurements at higher resolution from ACT. You should see that the maps basically agree, except for the ACT data, because more modern data is higher resolution, higher sensitivity. And that higher resolution and higher sensitivity lets us detect both point sources, often quasars and radio sources, those red dots, but also clusters of galaxies, which show up blue in this map, casting their shadows against the microwave sky. We take this data, we measure the second moment, the amplitude of fluctuations and variance equivalently of the map as a function of scale. And that's the data shown here. The green points are from the WMAP experiment from the early 2000s, the red from the Planck experiment, the yellow and blue from the ACT experiment and the South Pole telescope. And the takeaway you should have from this is, one, the experiments agree. They're seeing the same basic fluctuations with the same basic properties. The combination of experiments cover a very wide range of scale. And what you should also see subtly in this plot is the dashed line that goes, which is our model. And the data shows a pretty complex structure, and the model fits the data. We fit not only temperature, but polarization. I don't really have time to talk about polarization. And just turn in the final minutes to our efforts to take that data and determine the basic parameters of the universe. And here we list the basic parameters: the density of matter, the density of atoms, so on. And we're interested not just to measure those parameters, but to ask some more fundamental questions like, what is the nature of dark energy? Determines the masses of neutrinos? How fast is the universe expanding? And by making these measurements, we make progress towards answering these questions. And when I've shown you those maps as correlation functions, I think a better way to just visualize what's going on is a stacked temperature fluctuation map. So what's shown here is you take the maps you saw, you go back to those maps again. Here's the all sky maps. You take these maps, you take every hot spot on the map, every maxima, and you stack around those maxima. And you can see that the maxima, every hot spot here, is surrounded by a cold ring. Every cold spot is surrounded by a hot ring. And by measuring the properties of the patterns we see around hot and cold spots, which is equivalent to measuring the 2-point statistics, we can infer the basic properties of the universe. The distance between the hot spot and the cold ring is a ruler. It represents how far a sound wave can move in the age of the universe. And since we know what that is, that lets us determine, since we have a ruler we're holding up, we could figure out how far away it is. That lets us determine the age of the universe. The relative amplitude of this hot spot and the cold ring depend on the density of atoms, and in fact, most importantly, on the ratio of the density of matter to the density of atoms. And the thickness of that ring depends on things like the density of atoms, which determines the diffusion rate. So what's plotted above is the observations. What's plotted below is our best fit model. You can see the model very nicely matches the observations. There's stacks of both temperature and polarization. And when we say our curve fits the data, the dashed curve fitting the points here, that's equivalent to having a nice visual match here. So effectively, one's just the Fourier transform of the other. This is some even more modern data showing data from a number of different experiments, model and theory, measurements of both temperature and polarization, and also the correlation between temperature and polarization. And the takeaway you should have from this plot is a very successful model where the model fits the data. So given that, what do we want to do next? Well, we want to compute the parameters. And this shows what happens when we go to those equations we talked about at the beginning of the lecture and compute our parameters. And you can see the basic parameters of the universe here. What's shown is the density of atoms, the amplitude of fluctuations, how those amplitudes depend on scale, how fast the universe is expanding, how lumpy it is. And what you see here in these different colors are measurements from the WMAP data, the Planck data, the ground-based ACT data, and you should see that the basic parameters are really consistent. And these 1D plots shown on the edge shows what happens if you marginalize over all of the other parameters to get a 1D likelihood and get the best determined value for things like the density of matter in the universe, how lumpy it is, how fast it's expanding, and so on. And this shows both the 2D projections of the likelihood and how they, what happens when we do marginalization. I'll just skip ahead. For those of you who want to get your hands dirty and try this, these links, and I can provide them in the chat if people like, will give you access to code where you can take the data, run some Python scripts, and compute these yourself and see how we compute the likelihoods. So I could go on and talk a bit more about the details of how we do this, but I'd first like to stop here since we still have a little bit of time and see if people have questions on some of the material that I've already covered in this lecture. So why don't I stop here and take some questions before adding some final comments. I don't know how you want to take questions here. So I'm looking at the chat, and there's a question from Jiri Pishing, sorry if I mispronounced your name, asking how fast is the universe expanding? Our best estimates for the expansion rate range from about 68 kilometers per megaparsec to about 72 kilometers per megaparsec. And that uncertainty, we actually get different results from different ways of measuring it. I think the 68 value is the most robust one, and that corresponds to a universe whose age is about 13.8 billion years. The second question is, since the universe is expanding, Hawking made us know that the law of thermodynamics is expanding. Can disorder cause earthquakes and other natural disasters? Well, the expansion of the universe, the disorder, the entropy, actually just keeps the universe very simple. The expanding universe, it's well described by a thermal distribution. It's what we're seeing from that expansion today is this microwave background. That's material whose temperature is about 3 degrees Kelvin. That microwave background, while it's detectable on Earth, and some of you may have accidentally heard it or even seen it, if you listen to your radio between channels, about 1% of the static is due to the microwave background. If you watch TV and you don't have cable and are switching between channels, that accounts for some of your static images on the TV. But it doesn't do much beyond that. So things like earthquakes are pent-up energy from the motion of plates on the Earth. The source of that energy and those motions is actually the Earth's cooling and does have to do with radioactivity, the Earth's core. So in a sense, you can trace that back to material that formed in stars, but the direct link to the Big Bang is pretty weak. Next question from John. What's causing the universe to expand? Well, one of the interesting predictions of general relativity is for a uniform universe, that the universe will either expand or contract. And so I think you can think of just the density of the universe itself and the properties of space-time as driving its expansion. It's not really expanding into anything. It's just that the distance between things are growing. I like to think about it as expanding into the future. And then John asked about the universe's fate. This is in general relativity, there's sort of two potential fates. There's actually a poem about this by Robert Frost, who learned about cosmology from Harlow Shapley when they were both professors at Harvard. The poet wrote, "Some say the world will end in fire, others say in ice. I think I know of enough of desire to think that the world will end in fire. However, I know enough of hate to think that ice will suffice." Our current best ideas based on the current data is that the universe will expand forever, getting ever colder and colder, less and less dense. Yes, the answer to can we relate redshift to Hubble's law is yes. Questions on some additional materials for understanding. Of course, this really depends on the level you want to come at the material. For a broad introduction at the graduate level to general relativity and to its applications in cosmology, I'd recommend Liddell's book on cosmology, Liddle, or John Peacock's book on cosmological physics. Lots of questions. Let's see.
Yeah, I think we still have some questions.
Yep, I'm looking at the questions. Sorry, they're coming in quickly enough on the chat. The heat death is unavoidable. Well, I think our choices is either the universe will expand, die in a heat death, or will eventually collapse in a hot big crunch. What if the Big Bang Theory is not the origin of the universe? This is a very interesting question. What we really have evidence for is that the universe is expanding today. We then take our evidence of the expansion that we see in the motions of galaxies, run it back in time, and realize it leads to an infinite density. And they're really, in a sense, two classes of theories to talk about what the universe's beginnings. One is to say that the universe had a beginning, that time started with the Big Bang. And asking what was before the Big Bang is like asking what was north of the North Pole. And this is the idea that Stephen Hawking, for example, preferred, that the universe had a beginning and emerged from some quantum initial conditions. Another possibility is the universe has been around forever and has gone through a series of collapses and re-expansions and collapses and re-expansions. And one of the things that's an active area of research in cosmology is both exploring the theories and the potential observations that can distinguish between those two different origins. How does the magnetic field affect expansion? Magnetic fields, because they have energy associated with them, do affect the expansion of the universe. We think that the magnetic fields in the early universe are fairly weak, so their effects were relatively small. So one question is about, does the map cover the observable universe? In fact, yes, because you look out in space and time about 13.8 billion years in all directions, and what you're seeing in the microwave background, I think of it as that sphere around us. And then this question about the patterns providing clues to the nature of dark matter and energy of the universe? The answer is yes. It does provide some clues. It gives us the measurements of their abundance. It also tells us, or at least constrains, how dark matter and dark energy interact with radiation and with ordinary matter. And yeah. So next question, how do we know or ensure that all the parameters of the model account for the actual parameters in reality? This is a very good question. For any given set of model, we can ask what's its best fit to the data. Then we go and we consider alternative models that have additional parameters or different parameters. And we see if those provide a better fit for the data. And it's by comparing models that we can determine which ones are the preferred model given the data. There's really not much relationship between the geometry of the Earth. The Earth's geometry is, of course, close to spherical, slightly oblate, a bit bigger at the equator. The Earth's geometry is really determined by the balance between the gravity, which tends to want to make things spherical, and the strength of materials like mountains, which want to allow for asphericities. That's why we have, the heights of mountains like Mount Everest is basically determined as a balance between gravity and strength of materials. On the other hand, the geometry of the universe is determined by the balance between the expansion rate of the universe and the density of atoms. One of the questions about the expansion is, what does it mean about things? Because the expansion is accelerating, it actually means that many of the distant galaxies we see today will not be visible in the future. So why is the Hubble constant varying? Well, as the universe expands, the Hubble constant changes with time. As the universe expands, typically we expect the Hubble constant to drop with time as gravity slows the expansion rate of the universe. So that's why it's changing with time. The Hubble, well, when you see values between 65 and 80 for the kilometers per second per megaparsec, what that's doing is that's reflecting that different ways of measuring the Hubble constant give us different values. And a very active area of research is understanding if those differences reflect uncertainties or errors in the measurements, or whether those differences reflect real physical differences that are pointing at a failure of the model. How do we account for dark matter and the great attractor? Well, that's actually one of the things we do, and we take our basic theory and we look how it works with gravity and atoms, as we look and see, can it produce the large-scale structure of the universe? That's a question that let me take in my second lecture, because I'm going to be talking much more about large-scale structure in the second lecture. We're getting close to the end, so let me bring this to a close. Thank you for your attention, for your excellent questions, and look forward to talking to you all later this week. So let me stop there. Thank you.
Yes, thank you very much, Prof. It's a privilege to have you. We're really, really excited. It's a very brilliant thing to have had you. I think a lot of persons joined from different universities. We have some universities even joined from Ghana and one from Kenya too. So it's really good to have you, sir. Thank you so much, Prof. Thank you.
And look forward to seeing you all on Friday. So
yes, thank you.
Okay. Enjoy. See you. Have a good week till then, and see you then.
Yes, thank you, Prof. Sorry, I have a last thing to say. So I think I've been getting direct messages. Some persons are asking for how they are going to get the lecture notes.
I thought I would
That's
email them to you after this lecture,
oh, all right. Yeah.
and then if you could share them with people.
Yeah.
So I have your email address. I'll send that to you momentarily.
All right, Prof. Thank you very much.
Sure.
All right.
Yeah, bye.